everyone. Today I will be talking about following select statements through Citus internals. And in fact, what does it mean that what we will look into what happens under the hood when a user comes in and types a select query. And then we will, while doing that, we will also have an opportunity to discuss some basic architectural diagrams of Citus. Okay, so before going into the details, so first I wanted to just describe myself. So my name is Onder Kalaci, and I have been working on Citus almost 8 years now. So I also added and Postgres in the parentheses because when you work on Citus extension, you're actually working very closely with Postgres code base as well. So I count myself working on Citus and Postgres at the same time. And I had the opportunity to work on various parts of Citus extension, which includes the parts that today I will be talking about. And currently I'm a principal software engineer at Microsoft, working on Citus database extension, the open source extension. Okay, so before describing how, what happens under the hood for Citus, I thought it would be very useful to remind what happens for Postgres under the hood when a query comes in. So the query processing in Postgres consists of almost 4 distinct stages: parse, analyze, rewrite, plan, and execute. So very briefly, parsing means user types in a SQL query, like in a text format, and then parsing is just getting that SQL command and converting it into an internal data structure for further processing, like internal C data structure, which is just representation of the same text in the memory with a C structure. And then in the second stage is called analyze and rewrite. So analyze is mostly making sure that the query is semantically correct. For example, if a user tries to select from a non-existing table, Postgres will complain, saying that, okay, this table does not exist. Or similarly, if, for example, the var clause of the query should include a Boolean value, it should either return true for a row or false, so that the Postgres returns that row or not to the user. And then, for example, in the query, if you let an integer value on the var clause or text value in the var clause, the analyzer will complain, saying that, okay, you should have Boolean column. So these type of checks are done in the analyze section. And then the rewrite is more about rules and views. So when a user creates a view, the view is underlying. There's a underlying query that created the view. And then if that view is used inside a query, then during this stage of query processing, Postgres replaces that view definition, view keyword with the query that the view is actually created. So these kind of transformations happens at this time. And then the third stage is planning. So planning is probably the most complicated and most comprehensive part of the query processing from Postgres' perspective. And then the idea is that the planner generates a plan so that the executor can follow the plan to return to execute the query. And then the main idea behind the Postgres planner is that, so for example, if you select from a table, the table might have an index or might not have an index, or if there are aggregates in the query, so the aggregate could be an hash aggregate or group aggregate, or if you have multiple tables joined in the table or subqueries, then which order the subqueries or joins should be executed. If, like, for example, should table A be joined with table B first, or A with C, or B with C? Like there are plenty of combinations that a query can be executed, can be planned. And then Postgres' planner Postgres has a cost-based planner optimizer, which assigns some costs to each of these operations and then tries to pick the optimal one. And then executor is actually relatively simple. So it follows what the planner yielded, and it recursively calls these plan nodes over and over again to fetch tuples from nodes to the upper level nodes, and then finally just return the results to the user. Okay, Citus's query processing phases are the same with Postgres, and the main difference is that Postgres allows users and its extensions to extend its capabilities, and then at this point, Citus extends the planner and executor parts of this this flow. So the extended planner yields a distributed plan, and the extended executor gets a distributed plan and does a distributed execution, which we will double click on them in the future slides. So maybe half a step back. So one of the design principles behind Postgres is its extensibility. So in very basic terms, so as a user can create a new type, or as an extension, extensions can extend the Postgres's capabilities through some APIs, which are internally called hooks. And it's really out of scope to discuss the specifics of these APIs and like other means of Postgres's extensibility. But for interested readers, I also added some slides at the end, at the appendix section, for showing which API Citus use and how it uses briefly. Okay. Also, before double-clicking on the planner and executor, this distributed planner and distributed executor, I just wanted to briefly remind the architecture of Citus. So the user comes in and types a query, right? And then the parser and the analyzer are the same with Postgres. And then when it comes to the distributed planner, on the coordinator, so there are some metadata tables that Citus keeps track about how the data is distributed in the cluster. And then on the workers, there are shards, which are just regular Postgres tables, and the metadata keeps track of which shard is on which node, and then which data fragment is on which shard. And depending on that, the planner tries to come up with the optimal plans, which I will describe later. Okay. So Citus's plan and execution nodes are represented within Postgres's execution and plan nodes. So from Postgres's perspective, Citus's objects and Citus's objects and structures and Citus's representation is a first-class object from Postgres's perspective. So the main difference that Citus adds on top of Postgres's planner is the concept called task. So task is just a SQL command that can be executed on shards. So they are just regular SQL commands that are executed on the shards. And then the distributed planner could have like one or multiple tasks, and then the distributed execution executes these tasks on the shards and then returns tuples back to the node which initiated the distributed query. Okay, now let's maybe zoom a little bit into the planner. So when you look at so as I mentioned, so Citus's planning infrastructure is just like first-class objects in the Postgres's perspective. And if you look into this whole plan, it's really almost indistinguishable from Postgres's plan. So there are some additional things that we will go into, but I mean, the actual plan is just like a regular Postgres plan. So the first thing that we can look is the task. So task is the smallest execution unit in Citus's execution. And then task is basically a SQL command which is executed on the shards, which are regular Postgres tables. And then the distributed plan can have one or multiple tasks. So for example, if user runs an aggregate query across all shards, then this means that this query needs to touch across all the shards, meaning that it will have number of shards tasks. But for example, if you are selecting from a distributed table, but also adding a distribution key filter to the query, then the planner understands that, okay, this query only needs to access the data on one shard, and it only creates a single shard. And then for certain queries, so after running the tasks, there is an optional, optional meaning that for certain queries, there is an additional aggregation step needed. So, which I will double click in the next slide. Okay, first, again, discuss the concept of task a little bit further. So as I mentioned, so task is just a regular SQL command that is generated on the coordinator, which is responsible for creating the results for the user for some subset of the data, like from over a single shard or over a set of collocated shards. And then, so we created SQL command and we just run it on a regular Postgres table. So the rest is really handled by Postgres. So once the tasks are created and sent to the relevant nodes, then the rest is handled by Postgres. And this gives some advantages to Citus. So Postgres already knows about indexes and statistics and how to plan this query. And then by sending SQL commands to the shards, Citus can utilize all the information and all the optimizations and whatever Postgres does directly by using the same API that a regular user would use. Okay, let's then zoom into the coordinator plan. So as I mentioned, for certain queries, for example, if you want to calculate the average of one column across all the shards on a distributed table, so the shard needs the query needs to access all the shards in the cluster. So for example, say in this case there are 32 shards, and then from these 32 shards, all the shards are accessed. And when we are calculating the average, we cannot just push down the average to the shards. So what we need to do is we need to get all the sums from the shards and also all the counts from the shards. And then we should calculate the average on the coordinator as a final step by summing the sums and summing the counts and then dividing these two. So these kind of final aggregations and final operations are done on the coordinator. And then this operation is also very purely integrated into Postgres. So we are just telling Postgres, saying that, okay, so these columns are coming from the worker nodes, and then we want this kind of query to be executed on the coordinator, and then we let Postgres to plan and execute the rest for us. So, okay, so now I have described the basics of the distributed planner, and then the second phase is the distributed execution. So the goal of the distributed execution is to execute the tasks, and the tasks are the SQL commands. And in the end, get all the returning tuples from the shards and then just fed it to the coordinator. If there's an optional aggregation step, do that, and otherwise just return the result to the user. Okay, so again, we described, so some distributed plans consist of a single task and some from multiple tasks. So the executor, maybe I can explain it why we call this executor as an adaptive executor, because the executor is smart enough to adapt the different workloads. So for example, for lots of multi-tenant use cases or CRUD workloads or OLTP workloads, the distributed plans typically yield a single task. And for other workloads, such as real-time analytics or HTAP or time series workloads, it's typically the planner yields multiple tasks. And then the executor is designed in a way that it can automatically adapt the query and the workload per query basis. And on top of that, the adaptive executor can also adapt the network latencies and the task execution times and like the actual task executions, and like depending on many like many different parameters. And then in general, the connection establishments can be costly in Postgres. So because, I mean, if you have an index, for example, on a table, and then if you run a query using that index, for example, the query execution on the shard or on Postgres table could be like less than 1 millisecond. But if you try to establish a connection, especially under heavy loads, then the connection establishment times could sometimes dominate the total execution times. And to avoid that, Citus caches one connection per node, and the executor does that caching. Okay, so when there's a single task, actually, it was easy to just route that task and wait Postgres to return the tuples. But then if there are multiple tasks, that is where the adaptive executor shines, and there are things to describe and discuss a little bit further. So the executor creates a pool of connections per worker node, over which it can parallelize the task executions. Remember that one of the value propositions and important part of Citus is that its ability to parallelize tasks, parallelize queries across shards. And then this is how it happens. So it creates a pool of connections per node, and then as soon as the tasks are available, those tasks are assigned over these pools. And then we actually mimicked TCP slow start algorithm. So how does TCP slow start? Maybe if you are not familiar, so TCP slow start algorithm is it mainly adapts the available bandwidth and avoid congestion. So it starts, for example, sending few packets, and then if it gets response, and then it increases the packet send, and then as long as the remote side responses, the sender increases the bandwidth as much as possible. So this is really what we use in the adaptive executor. And in the next slides, I will show some examples of how these mechanisms work. Okay, so at the start, as I said, so there is one cached connection, so the executor immediately starts executing the tasks. And then if the tasks are not finished in 10 milliseconds, then the executor decides to establish one more connection. And then if after 20 milliseconds, if the execution is not finished yet, then the executor decides to establish even more connections. Then it doubles it, and it actually increases one, and then it opens two more connections. And then it goes like this. In every 10 milliseconds, the executor keeps opening more connections. So basically, if the queries are short queries, like 1 millisecond or less than 1 millisecond queries, then the connection overhead is minimal, because the executor can reuse the same existing connection for multiple tasks, and then that's why it doesn't need to establish new connections. But then if the queries are taking long, say the tasks are, I don't know, in the orders of seconds, and then in really less than 100 milliseconds, then the executor will realize that the tasks are taking too long, and then almost all tasks are already be parallelized across the shards. And then, of course, this 10 millisecond is not hard-coded, and then even there is more smartness in the executor, which I just think maybe it's too much detail to discuss, but it's not just like static 10 millisecond, but it also takes into account, okay, how does the tasks that happened in this execution took, like how much time they took and how much connection establishment took, and then does some smart calculations based on that as well. Okay, this is the first example of slow start and how the executor works. So in this example, assume that the tasks are really quick tasks, like less than maybe 1 millisecond tasks. So the executor assigns the task to the already cached connection, and then the task is finished, and then the executor pulls the next task, and keeps running it, and then it also finishes, and then the third task, and then the fourth task. So in this example, for example, the executor does not need to establish new connections, which is really useful in, especially with high concurrent environment, because we are just talking about one session in this example, but then there are multiple concurrent sessions running multiple distributed queries. So we should not be, we should refrain from establishing too many connections. Okay, in this second example, let's assume that the task execution times are in the orders of seconds. So, for example, the first task is assigned to already established connection, and then after 10 milliseconds, the executor realizes that, okay, the task has not finished, but then we have still many tasks to assign. So then it builds up 2 more connections. And then once those connections are established, the 2 tasks are pulled from the queue, and then they started running parallel across the first one. And then after another 10 milliseconds, the executor decided, okay, the fourth task also has not been assigned to any pool yet. Then it establishes a new connection and then assigns the task over that connection. And then as the tasks finish, the executor just closes the existing connections, but only keeps the one cached one. Okay. So I think I'm at the end of my presentation. So this is my last slide, and I wanted to just talk again what we discussed. So the first thing is that Citus's planning and execution is done as a first-class operation from Postgres' perspective. So all the objects that Citus introduces into the Postgres is just represented as if any other Postgres structure. And the second is that the user's input SQL query is actually split into multiple SQL queries by the coordinator, which actually tries to push as much as computation down to the shards, but then pull as less data as possible to the coordinator. So this kind of optimization is done, and these are done through some actual SQL queries, and then the SQL queries are just tasks which are sent to shards. And then the third bullet is that the executor's main aim is to balance the number of connections and the total execution time. So the executor tries to establish as less connections as possible, but also tries to, at the same time, optimize the shortest execution times for the queries. And that's all for me. Thanks for listening.